Okay, so here's the next set of questions then, 11 to 20. So we crack on these. So which species breaks the octet rule here? Well, PCl3, that's just basically your trigonal pyramidal one, so these put down quite quick and easy. Then so I think, okay, so it's not that one, because phosphorus is a B in the octet rule there. Boron Tetrafluoride, again, that's basically tetrahedral. With boron, again, a B in the octet rule here. Boron doesn't have to obey the octet rule. BF3, for example, breaks the octet rule because it's only got 6 electrons around the boron, but that's how boron can act as a Lewis acid and accept a pair of electrons from a fluoride ion, so one of these would be a coordinate bond. SCl4, this one's looking the likely one. I know it's not going to be NH4+, because nitrogen has to obey the octet rule. NH4+ would be basically the same as this, a nitrogen with 4 hydrogens and then positive charge. So SCl4, just to go back to basics on this one a little. So SCl4, that's 1 sulfur from group 6, plus then you've got 4 chlorines, so it's 4 times 7. 4 7's 28 plus 6, that's 34 electrons. Now, if we divide that by 8, that gives 32, so 4 bonds, and you have a remainder of 2, which therefore is 1 lone pair. So we can see already it's going to be this one, that sulfur is going to be breaking the octet rule because it's got 4 bonding pairs plus 1 lone pair, so that sulfur is actually going to be a seesaw shape. Not that it actually wants that, but got to cover a bit of the other chemistry. This, of course, is the 5th position if it was trigonal bipyramidal, but with a lone pair of electrons there, then it looks a bit like a kind of seesaw if you turn it that way. So we're going to go with C. Number 12, which compound contains both ionic and covalent bonds? Well, silicon tetrahydride or silane. That's an incredibly flammable compound. It's a pyrophoric, which means it just catches light on exposure to air. Dr. Foley asked the technician to make it once and she wisely refused. So those are just covalent bonds. Sodium nitrate, that's the one I'm going to be going for because it's got Na plus ions and nitrate ions. And then, of course, in the nitrate, you've got covalent bonds between the nitrogen and the oxygens. Of course, one of these would be a coordinate bond as well, but in reality, remember, it would be a resonance hybrid. All 3 bonds would be the same length and the same strength, but you've got ionic bonds between the 2 ions, but you've got covalent bonds within the molecule, nitrate ion itself. This one would just be covalent bonds. It would actually just be C double bond O, a couple of hydrogens, and then this would be an ionic compound, S2- and 2 Na plus ions. I'm going to go with B. Which of the following are van der Waals forces? So van der Waals is a kind of a term that's fallen out of favour a little. So A-level used to use it a lot, but basically it's your dipole-dipole forces and your London forces together, but not the hydrogen bonds. So it kind of includes 2 of the intermolecular forces. So we're looking for 1 and 3 only, so that will be B. In which group do both compounds contain delocalized electrons? So again, have a bit of a scan through. Now you'll recognise C6H6 is benzene, so that does have a ring of delocalized electrons, remember. And sodium hydrogen carbonate, well, it's an Na plus ion, but then you've also got HC, oh, what am I doing? You've got OH, so that'll be your hydrogen carbonate ion. And then, of course, these electrons are delocalized because a lone pair of electrons can come in here and kick a pair of electrons out onto the oxygen. So again, in reality, both of these carbon-oxygen bonds will be the same length and the same strength. So it's going to be this one. In this case, the carbonate ion is present, so that would have delocalization, but not the sodium hydroxide. In this one, it's C6H10, which that's quite a lot less, actually. That's not an alkene. Because of the hydrogen to carbon ratio, it's not CnH2n, this one is, so this one looks like an alkene, so that could be pentene, for example, or cyclopentane. This one would have to be either a diene, so there could be 2 carbon-carbon double bonds in the molecule. Alternatively, there could be a triple bond, or it could be a cyclic alkene. Would be another possibility, but whatever it is, there's no delocalized electrons in this system for us to worry about. And again, in this one, well, yes, the hydrogen carbonate ion does have delocalization, but C6H12, well, that's either hexene with an isolated double bond or cyclohexane, so that does not have delocalization. So we're looking for C. Which of the following is correct? Okay, so here we've got ethyne, so A equals this stuff. So number of electron domains 2. Oh yeah, just looking on the carbon. So 1 domain, 2 domains. So that's fine. That's right. Linear shape. Yes, it is. Bond angle of 180. Hybridization you haven't covered yet. That's something we'll be covering in the near future. But when you see a triple bond, that's a good evidence of sp hybridization. So it looks like we've already kind of lucked up on the answer here. Just to quickly flag through the others. Here B, you've got that is ethane. 4 electron domains around each carbon. Yes, that's correct. Square planar, that's not correct. The molecular geometry around each carbon would be tetrahedral rather than square planar, so that's not correct. And then sp3, when you see single bonds, then yes, we've got sp3 there. So that is correct, but it's not square planar. The ammonia in NH3, looking at that one, lone pair of electrons on the nitrogen. So there's not 3 electron domains around the nitrogen, there's 3 bonding pairs plus 1 lone pair, so that's wrong, there's actually 4. The shape is trigonal pyramidal, and again there's single bonds, it is sp3, that's correct, but that first bit's wrong. And then lastly, let's consider water. So yes, there are 4 electron domains around the molecule, around the oxygen. It is a bent shape. But it's not sp2. Again, we just got single bonds here. It's actually sp3. So we want A as the right answer. Okay, number 16, Hess cycles. There's a few approaches to these. You can kind of try to create the Hess cycle, but a nice way, which I quite like and is quite straightforward, is just to kind of like logically arrange these equations based on whether they are reactants or whether they are products and how many there are. So what we've got, for example, is, okay, we've got 2 carbons in the equation. This one here features carbon. Now it's on the left-hand side, which is good. That's where we want it. It's a reactant, but there's not enough of them. I need twice as many because there's 2 carbons. So I'm going to have 2 times minus 394. And then, okay, how do these other equations feature? Well, there's hydrogen here, and hydrogen is a reactant. Here, hydrogen's a reactant. So this equation is the right way around. That's fine. I don't have to flip it. But I basically need half of what's going on here because I just want the 1 hydrogen. So that's going to be plus half times minus 572. And then what about this last equation then? Well, here we've got the C2H2, but it's on the wrong side. It's a reactant. I need it on the right-hand side to be the same as here, to be a product. And also I've got 2 there, I just want the 1 in the equation. So again, what I'm going to have to do with this one is I'm going to have to flip it, so it's reversed. So this will become plus 2602, and then again I'm going to have to halve that. So that's going to become plus a half times plus 2602. So let's see which looks like the best match. Well, obviously not this one, because yes, it is 2 times minus 394, but we don't have the halves. And similarly again here, it's not going to be this one. So which of these matches up correctly? So 2 times minus 394 plus a half times minus 572 is looking good so far. Minus a half times minus 2602. Now that looks like that will actually give the right sum I want, because minus times a minus is then effectively going to make this a plus, which is what we'd want from this equation here. Whereas in this one, the first bit's the same, but then if we did plus a half times minus 2602, we can see that bit's obviously not right. So it's a little bit confusing the way they presented it there, but this is the one we want, because minus times a minus would be the same as effectively a plus times a plus. It'll become a plus, that's right. Number 17, which equation represents the average bond enthalpy of the silicon-hydrogen bond in SiH4? So they're all forming atoms apart from this one. It's definitely not this one, because whenever you look at bond enthalpies, you're basically sort of you're tearing atoms off things. Now in this one here, that would be the specific bond enthalpy for removing the first hydrogen. So that's not going to be the case, because I want the average bond enthalpy, because in total there's 4 hydrogens attached to this silicon, so I'm going to remove all 4, and then because it's an average I'll have to divide that by 4. So it's looking like between these last ones here, so this one's not going to be the average one, this is going to be the total bond enthalpy for removing all 4 hydrogens. So I want this one here, where basically I take off all 4 hydrogens, a bit like here, but then I've just divided everything by 4 to give me this equation to find that average. So we want B. Which transition represents an entropy of hydration? So remember, that's where we take something and dissolve it in water. So, but it's got to be a gaseous ion as well, don't forget. So here, this is an entropy of solution. So even though we're taking something and dissolving it in water, that's an entropy of solution. So that's not correct. So we're looking between these two, because this one is basically you've got a bond break in there. So this is where you've got sort of a water molecule stealing a hydrogen from another one. So we're forming an OH bond and breaking that one there. So we're not going with this one. So it's between these two. So it's got to be an ion, and it's also got to be a gaseous ion is the definition for an entropy of hydration. So it's the entropy change when 1 mole of gaseous ions is dissolved in water to form an infinitely dilute solution. So I'm going to go with D, because I want a gaseous ion to start with. 19, what are the signs for the entropy changes associated with this reaction? I like entropy, but it's been a while since I've taught it, so I have to think through. So you've got delta S surroundings. Remember, that's to do with whether it's exo or endo. And then delta S of the system, that's to do with whether the system is becoming more or less disordered, or more or less ordered, however you want to put that. So remember, a positive entropy change is going to lead to something becoming more feasible, because if you remember, delta G equals delta H minus T delta S. So negative delta H always helps us, which is where it comes in from the delta S surroundings, and then T delta S, that's where we've got temperature, and then that's where if delta S is positive, that's always going to be good, because that is only going to make delta G more negative. It's when delta S is negative, then that can make delta G positive above a certain temperature, because obviously delta S is usually quite small, but it's amplified by the temperature. So let's make a bit more sense of what's going on here. So we've got steam condensing to form water. Now remember, steam is at a higher energy than liquid water, because if you want to go in the opposite direction, you're basically boiling a kettle, that's putting energy in, which would be endothermic. So the forward reaction is exothermic, and that's why it hurts if you put your hands in steam, because it transfers lots of heat energy to you. So exothermic, that would be a positive yeah, that's right. So if it's exothermic, that's going to lead to a positive entropy change towards the surroundings. So I'm going to rule out these two. And then it's actually, the molecules are coming together now and forming not a regular lattice as such, but they are becoming much more ordered, the molecules in a liquid, where they're all combined rather than when they're all flying around in a gas. So there is a decrease in entropy as we go from a highly disordered gaseous state to a more ordered water state. So I'll be looking for a negative change in the entropy of the system itself. So I'd be going for A. And then number 20, we've got a bit of a rates question. So graph 1 shows a plot of volume of CO2 against time for the reaction of calcium carbonate with 1 mole of hydrochloric acid. The acid is the limiting reagent and entirely covers the lumps of calcium carbonate. Which set of conditions is most likely to give the data? Sorry, I'm thinking about something else a minute, playing the chasers. Graph 1 shows a plot of volume of CO2 against the time for the reaction of calcium carbonate with 1 mole of acid. The acid is the limiting reagent, entirely covers the lumps of calcium carbonate, so we reach the same point. Yeah. Which set of conditions is most likely to give the data plotted in graph 2 when the same mass of calcium carbonate is reacted with the same volume of hydrochloric acid at the same temperature? Okay, so temperature is the same. So what have we got? We've got a reaction which is faster. Now if it's faster, it must be that there are smaller lumps of calcium carbonate being used. And then coming back to this bit here, it said, okay, we've got 1 molar HCl, and that the acid is the limiting reagent. So if we change the concentration, in this particular case, so if we change the concentration, well, firstly, that's going to make it slower, so that doesn't really make any sense, and also we wouldn't then reach the same point. So in this one, I'd probably be looking for a line which is more this side, and then ends up finishing about halfway. So I'm going to be going smaller and the same concentration and volume, so that should lead to a faster reaction with the same volume of carbon dioxide gas produced. It's a little odd, really. I thought they might have sort of fine. Yeah, okay.